So yeah, I'm Niklas, and I will kick off this presentation with a bit of motivation and introduction to the ideas that inspired our work on generative pseudo-force fields, or also in short, GPFF. And then later on, Stefan will take over and explain the method and some experimental results in more detail. So since this is a seminar series on generative models, I think I don't really have to provide much motivation on why generative models are super exciting and very promising for all kinds of applications where speeding up the discovery of molecules or materials is important, for example, in drug design. So I'll directly start with basically framing the problem setting that we're tackling with our method GPFF. So we're assuming that our goal is to sample 3D molecular structures. So the molecules are represented as atom positions in a 3D space, XYZ coordinates, and atom types. So we're not dealing with molecular graphs. Of course, there also exist many applications and data sets with molecular graphs where it would be interesting, and there exist many generative models, but we're assuming that we're directly working with the 3D structure and that we have data of this. And the stable structures are local minima of the potential energy surface, which I will be talking a bit more about in a few seconds. What we're not looking at is sometimes confused is molecular dynamics. So this basically tells you how the atoms move in space over time, how they wiggle around these stable configurations or change from one to the other configuration. And yeah, this is something that also could be speed up with generative models, but this is not the scope of the work that we are doing. We're basically interested in directly sampling the stable molecular structures with a cheap and fast and accurate method. And of course, directly sampling, just sampling the structures without any conditions or constraints is a bit boring. So of course, usually in the application, you have some constraints. For example, you might have a protein pocket and you want to find something that fits in there. So this is something that our approach also allows to have these spatial constraints, as you will see later on. Okay, so let's have a look at the potential energy surface. On the right-hand side, you can see a depiction of it. Basically, the idea is that if you move around positions of atoms in your molecule, you end up on a different point on the surface, which basically means that the energy differs. And for some configurations, we see that we have a local minimum in this surface, and these are then considered to be the stable structures. So we denote this energy function as E of x. So x is the molecule in our case. And of course, at these local minimas, the gradient of the energy will be zero. And there exist two basically established methods in machine learning that have been used for a long time in order to sample stable molecular configurations. And I will introduce them briefly in the following. I will start with machine learning force fields, which use relaxation. And then I will also talk a bit about a generative approach using diffusion models. And in the end, then I will contrast them and explain how we take the best of both of them to come up with our method. Okay, so machine learning force fields are pretty simple, actually. So if you have some kind of 3D molecular configuration, you can always use first principle methods like DFT to compute the energy and forces. Of course, this is very expensive, and for very large systems, maybe you cannot do it, but we just assume for the systems we're interested in, we can do it and generate a training data set. And nowadays, there exist actually kind of large training data sets and also many models specifically designed for this task of directly learning to fit the forces. So what are the forces? The forces are basically defined as the negative gradient of the energy. So they provide us with a vector on each atom that basically tells us how should we move these atoms to get the system into a configuration that is a bit more stable, that has a bit lower energy. And if we fit the model directly on predicting these forces, given the molecule as an input, we can then do relaxation, which basically means we start at some point with the system that is not yet stable, and then we just compute the forces and take a small step adjusting the positions according to the forces, and we repeat this until we end up in a state where the forces converge to zero. So this is the idea of machine learning force fields. Yeah. And in diffusion models, so this is another approach to do something very similar. Diffusion models are in general probabilistic models, which basically allow you to capture the distribution of a training data set. So for example, if you have a data set made only of stable molecules, the model should learn to assign high probability to a structure that is stable, and then lower probability to anything that is not stable. And in order to get these not stable data examples, what we do in diffusion is that we just augment our training data by adding Gaussian noise to the positions of the atoms. So in the first equation here, you can see that x0 is basically a reference system, a stable molecule from the data set. And what we do is that we add Gaussian noise, which is the epsilon vector, and this is scaled with a noise level sigma t. So we have different noise levels, and we add noise of different intensities to our data point to get augmented data. Sigma 1 is very small, so the positions are only slightly perturbed. You can still easily recognize the molecule. But as the time step, the t, increases, we increase the noise level, and then the system looks completely chaotic. And in the end, you cannot really identify the molecule it was coming from. And then the idea of diffusion models is that we basically train a model that gets a noisy structure and the time step t as input, and then predicts this vector epsilon of noise, which was added to the original system. And if we can do this, we can basically reverse this process, which means we can start from something that is completely noisy, drawn from a Gaussian distribution with the maximum amount of noise, like the highest noise level. And then we can slowly remove the noise and end up in some highly probable state, which then is a stable molecule. And in a probabilistic wording, this means that we basically compute the gradient of the distribution, probability distribution that the model has learned, which is called the score. And as we can see in the bottom box, the score can be computed from the noise level and the noise direction. And then you can use one of many sampling algorithms that have been proposed for diffusion models. Here you see the formula for the ancestral sampling in order to do this somewhat denoising process, which basically means increasing the probability of your sample by removing noise and then ending up in something that is a stable molecule. So in MLFFs, what we did is we minimize the energy, and here we maximize the probability, but both have the same goal in this formulation to find the stable systems. So let's look at them next to each other. We see that for training the MLFF, we basically need DFT computed forces. So this is very expensive and usually means that we have large data sets, but usually these are systems close to some equilibrium state. So we don't have labels for systems that are completely chaotic or very far away from being in equilibrium. So usually they can only be used close to something that is already stable because it's so expensive to compute these labels. In diffusion models, on the other hand, we don't need the DFT labels. We just perturb the systems, and this provides us with a signal to sample something that is stable. And this perturbation is so large that we basically cover a huge amount of space that the model can deal with. However, the problem is that we need a time step as an input. So if somebody comes to you and says, okay, here I have a molecular structure, and I think it's not yet stable, you don't know the amount of noise that is in this system. So you could not relax it with a diffusion model. You always need to start from the prior distribution where you know the noise level, and then you have to adhere to a fixed schedule and prior, and you need to put this time step into the model to do the sampling. On the other hand, the MLFFs, they don't require the time step. You could potentially start from any point in space, so it's very flexible. But as I said, usually the training data does not allow you to do this because you don't have data for all different kinds of configurations. So what we're doing in our work is basically combining the best of both worlds and trying to only keep the good parts. And luckily, there is a connection between the two that has already been explored before that we build upon. So if you have a potential energy surface, you can always get a probability distribution out of it by using the so-called Boltzmann distribution, which is basically an exponential function. And in the exponent, you have the energy that is assigned to your system by your potential energy surface. And in this way, you get a distribution where there is high probability at points that have a low energy in the potential energy surface. It's basically a direct mapping between the two, where the temperature T and the Boltzmann constant K define how flat or peaky this distribution is. And if you compare this to the variance exploding diffusion that I presented before, the distribution that is learned here is already very similar because we're adding Gaussian noise. The distribution that we're describing can also be or learning can be described by a Gaussian function, which has a very similar form, only that the energy function is basically replaced by this very simple term where we just look at the distance between the noisy sample x tilde and the reference sample x0. So we basically say we have a very simple energy that we can quickly compute, and then we get this simple probability distribution, and all the other terms can be matched depending on the variance and the noise level in the Gaussian of our diffusion process. And yeah, if you look at this, you see that we're already kind of close. Like these are very similar to each other. And yeah, Stefan will show in the following basically that we can combine the best of both worlds, that we just used equilibrium molecules for training and we augment them or noise them. And then we can still do flexible force-based sampling, like in a force field where we don't need the time step.
Okay, yeah, so thank you, Niklas. So now Niklas has already provided us with the key insight that the variance exploding noising kernel of diffusion models is secretly also a Boltzmann distribution for a very simple energy function, where the energy depends on the displacement between the non-equilibrium geometry and its corresponding equilibrium structure. And the temperature governs the noise level of this forward noising diffusion process. And so for the rest of this presentation, I want to take this idea and show how we can make a trainable model from this and how we can use this trainable model in order to sample stable molecules and also steer the generative process. So now if we look at this pseudo-potential energy surface here on the right, and we call this pseudo-potential energy surface because it's not a real physical potential energy surface, but it's like a simplified version which has its local minima at the same location as a real potential energy surface, like the physical potential energy surface, but everything in between is just much simpler. And now using this pseudo-potential energy surface, we can see here that the energy just depends on the displacement between noisy structure and its equilibrium structure. And we can easily derive the pseudo-forces by taking the derivative of this energy function with respect to the positions. And then we end up with pseudo-forces, which are effectively just the displacement vector between the non-equilibrium structure and its equilibrium structure. And yeah, now this is very easy to compute. And if we would have access to these pseudo-forces, we can easily recover the equilibrium structure x0 using the pseudo-forces and the positions of the noisy structure. But in practice, of course, if we have some random sample from somewhere, we don't know to which minimum it belongs. So we cannot just calculate this function if we don't have x0 at hand. But what we could do instead is to design a training loop and then train a neural network model in order to learn those pseudo-forces. And once the model is trained, we can use it for sampling new structures. And this effectively is our generative pseudo-force field, or GPFF. And the model contains like one diffusion-like part, which is the data augmentation. And then we have one machine learning force field-like part for training. And yeah, so if we look at the data augmentation part, we also start by sampling some equilibrium geometry, x0, and then we add Gaussian noise on an increasing schedule and end up with some perturbed geometries here. And this is exactly the diffusion forward process as it was explained by Niklas. And now based on these perturbed geometries, we can then do the machine learning force field-like training where we calculate the pseudo-forces, just as I explained on the slide before. And then we can take those pseudo-forces and just plug it into some standard MLFF style mean squared error loss function and train a model to regress on this loss function. And one important note here is that in diffusion models, we needed to provide the time step as an information to the model in order to learn. But here, since we view this as a force field now, and there is no such thing as a time step in machine learning force fields, we just skip this time step information here and don't provide it as an input to the model. And also, this approach in theory works with any machine learning force field architecture without needing to change anything there. So we just took the Payne neural network architecture that we have implemented in SNETPEG and just trained like any other machine learning force field task. Okay, so now I already explained that GPFF is somehow a machine learning force field and somehow a bit of a diffusion model. And we can show on this slide intuitively that actually GPFF is very much also a diffusion model if you view it from the right angle. So here we can see the forward noising process of a diffusion model on top and of GPFF on the bottom. And we can see that the data augmentation part is exactly the same. So we add Gaussian noise and we end up getting the same noisy structures here. But there's one key difference, and that is that the diffusion model learns these noise factors here in blue, which don't have any magnitude. So they have the same length independent of the noise level that we used. And in GPFF, we scale those noise factors with the magnitude, which means that if we are at large noise levels, so the structure is very perturbed, we end up with pseudo-forces with a high magnitude. And if we are at low noise levels, the magnitude of the pseudo-forces is very small, just like in standard machine learning force field models. And now, because our GPFF model learns this magnitude, and this magnitude also encodes the time step information somehow, right? So here for large time step, the model will predict something with a large magnitude, and for small time steps, it will predict something with a small magnitude. So just using this magnitude already is enough to encode the time step information. So we don't have to provide this as an additional input to the model. Okay, so now we know like the basic idea of GPFF and we know how to train it. And next I want to show how we can use GPFF in order to sample stable molecules from it. And because we can view GPFF as a diffusion model or as a machine learning force fields, we have a whole bunch of different options for sampling. And the most important part here is that we only need to train one single GPFF model, and it works for all different samplers that we will introduce. So first, we have the diffusion style sampling. And this is actually just the standard way of sampling in diffusion models. And this works because we can just calculate the score function here by scaling our pseudo-forces with a squared noise level sigma t. And once we obtain the score function, we can just plug it into any standard diffusion model sampler and use it to generate structures. And then on the other hand, we can also use the pseudo-forces and sample in some machine learning force field style and just follow the forces along towards the local minima, just as in standard machine learning force fields. But there's one difference, and this difference is that our pseudo-forces are so simple, so they just learn the displacement between noisy and not noisy. So what we can do is just follow one pseudo-force update step without any step size, and from this equation we end up at the equilibrium positions, at least in theory. And those are the two different approaches to generate new samples. And next, I will show them in a bit more detail and show some experiments that we did on QM9 for this. So yeah, first, diffusion sampling. So as I already said, this is just the standard way of sampling with diffusion models. So what we do is we sample a prior structure from some isotropic Gaussian distribution. And then we iteratively loop over this ancestral sampling update step, where we calculate the score by scaling the pseudo-forces. And now if we look at some results, we can see that it compares pretty well to a standard diffusion model using ancestral sampling. So here on the right side, we can see the validity of the structures depending on the number of function evaluations, NFE. So one function evaluation is one inference step of the model, so it provides a measure for computational cost during sampling. And as we can see, GPFF slightly outperforms the standard diffusion model while using the same number of parameters and the same hyperparameters here. Okay, and then next, I want to show some results on the machine learning force field style sampling. So we start similar to the diffusion model by just sampling a structure from the simple isotropic Gaussian noise distribution. And then we iteratively apply this prediction of equilibrium geometries. So this is the equation I showed on 2 slides ago. And because usually the model is not able to predict the stable geometry in one step, we can just iteratively loop over this and refine the intermediate structure with every step. And this is something that we can do with GPFF because we don't need the time step information. So if we would use the diffusion model and we would try to predict the clean geometry in one step, but then we don't really get the perfect result, then we cannot further refine it because the information on the time step is lost and we don't know how to further use the schedule. And also because we don't need this time step, we can also just freely modify those intermediate structures depending on what we want. This is something I will talk about on the following slides. But now first some results on this MLFF sampling. We called this MLFF style sampling direct denoising because we directly try to predict the equilibrium geometry. And here now on the right side, you can see in gray the results for a GPFF with direct denoising, and especially in the regime of low numbers of function evaluations, direct denoising clearly outperforms diffusion sampling with the GPFF and the diffusion model, and it converges to about the same validity for a large number of function evaluations. And so from diffusion models, we know that if we add a bit of stochasticity during sampling, usually the sampling quality improves a lot. So we also tried this for our direct denoising approach. And we can easily do this by just modifying this intermediate structure here on the left. So we make a prediction and then we add a bit of noise to this prediction, and this noise decreases with the number of steps. So if we converge towards the maximum number of steps, we don't add any more noise. And then at the beginning, we add more noise. And if we now look at the results, we can see that especially for the higher number of function evaluations, we get a much better performance, reaching 100% of valid molecules at about 256 function evaluations. So yeah, this now all looks pretty good, but validity isn't the only thing that matters. And we also investigated the sample quality in terms of distributional alignment to the QM9 target distribution. And here we can see that direct denoising with GPFF shows a strong bias towards compact and spherical structures. So on the slide, you can see the distribution of maximum pairwise distances sampled with GPFF and ancestral sampling compared to GPFF and stochastic direct denoising. And for ancestral sampling, we can see that we clearly match the QM9 target distribution, but for direct denoising, we have this bias towards lower maximum pairwise distances, which means that we sample more compact structures. So if the maximum pairwise distance is low, molecules are more like spherical, and if the maximum pairwise distance is large, it's more like long-chained molecules. Yeah, and actually, if you think about it, this is also somehow intuitive, because if we start denoising from the prior, and the prior doesn't have any information at all from which we could infer to which minimum it belongs, the model in the first step predicts some dataset mean-like structure, which is usually something round. And then using this round structure in the next step for refinement means that we stay in this regime of spherical structures. Yeah, so we observe the structure bias, but because GPFF is flexible, there is a kind of intuitive and easy fix for that. And I want to just showcase the idea on the slide. So imagine we have like one rod-shaped molecule and one disc-shaped molecule. Then we can see that that rod-shaped molecule is very elongated and the disc is flat and round. And if we want to sample like a rod-like molecule or some disc-like molecule, we could, for example, just start with a prior, which is already in that shape, right? So that's what we do here. We just sample some isotropic Gaussian noise, and then we just squeeze and stretch it to match the shape. And then we start from there and make a prediction with GPFF. And often this prediction may destroy the target shape, but we are able to just modify the intermediate structures. What we can just do is just take this prediction and squeeze it and stretch it to the target shape. And then we iteratively repeat this until we end up at those target shape molecules. And now in order to fix the distribution, we just trained a very simple model that learns the shapes of QM9. It takes about 10 seconds to train it. And then we can sample QM9 like molecule shapes and force them during sampling and yeah, try to fix the distribution. So here again, we have the sampling algorithm on the left. And just the new part here is that we stretch our intermediate structures, as I just explained. And if we now look at the results, we can see that we don't even have to sacrifice any validity here, but we even gain some validity at the low number of function evaluations regime, which is also intuitive because we start from something which is already closer to where we want to go. And yeah, now if we look at the sample distribution, we can see that compared to the standard direct denoising approach, enforcing the shape really recovers the distribution of maximum pairwise distances in QM9. And so we found the way to fix this distribution bias. And yeah, next we thought, okay, we cannot just use this as a fix for fixing this distribution bias, but this could also be a feature of our method, because we could just target any kinds of shapes that we're interested in. And so we tried this here with this intuitive steering approach. And the idea here is that we just mapped all molecules of QM9 onto this triangle of rod, sphere, and disk shapes. So rod is very elongated, sphere is like spherical compact structures, and disk structures are flat. And then we just provided an extreme target, like only rod structures or only sphere structures or only disk structures, and ran the generation. And we can see that we clearly match the target region pretty well without sacrificing any validity. So the validity is 98 or 99% still. Okay, and then we thought of going even one step further with our modification of intermediate structures. And we came up with just some demonstration of what is possible in theory, and combined this shape enforcement with a scaffold-based design. So here, the idea is that we define or build this interactive tool where in a couple of steps we iteratively build up our target molecule. And we start with some shaped prior structure. Then we generate a couple of samples. Here is 3 different samples. When we select one of those samples as a scaffold for the next step, and then we remove this one hydrogen atom here and place a shaped prior next to it, which is in this case a disk-shaped prior. Then we run the relaxation, and for the prior atoms, we enforce the shape, and for the scaffold atoms, we just don't update the positions. So if the model wants to move the atoms, we just set them back to their original positions. And yeah, then we end up with a set of more complex molecules. Here we select the first sample again as a new scaffold. We remove one hydrogen, we add a prior again, and then you can just iteratively do this until you find something interesting. And yeah, here we found this aspirin molecule in this demonstration, and just a small note. So aspirin is already out of distribution for QM9 because it has more than 9 heavy atoms. So this was also a bit of an extra challenge for the model. Okay, and with this, I want to wrap up. So the key takeaways are that we defined this generative pseudo-force field, which is a hybrid approach between machine learning force fields and diffusion models, where we don't need any DFT labels, we don't need the time-step conditioning, and we are very flexible. And with one model, we can use a whole set of different samplers. And those samplers also support things like intuitive steering with geometric or structural constraints. And yeah, as an outlook, which might be interesting for drug discovery, obviously, is to work on fitting molecules into protein pockets, for example. And we are mainly looking at materials generation right now, but also catalysis, large molecules, atom type generation, and so on might be interesting. And we are also currently trying to make a new version of our Snappack open source package and add this model in there too. So yeah, thanks for the attention, and we're happy to answer your questions.
Yeah, thank you very much, Niklas and Stefan. Now it's time for questions. So if anyone online has some questions, can do you have some questions?
Yeah, in the meantime, I can
I
also just ask a few. Yeah, it's really interesting to see these two ideas coming together. So thank you for the presentation. I guess I have a few questions just around like how. So you're actually kind of doing molecular generation here, but the focus was on a sort of force field, like conformer generation approach. How do you actually like infer the sort of atoms, atom types and bond types? Or is there an additional, are they also part of the sort of diffusion framework as well?
Yeah, so for this project, we only looked at atom positions and not atom type diffusion. So what we do is we just, during the experiments and sampling, we sample some structure from the test set, and then we destroy the positions by sampling them from Gaussian noise prior, but we still keep the atom types. So it's kind of guaranteed that there is at least one configuration which is valid for that. Yeah, so atom type diffusion is something which is certainly very interesting, but right now we haven't done this. And for here, in this example here, you can see the atom types are different in the molecules, right? So what we did here is that we just kind of randomly sampled different atom types and then ran the relaxation. But in this case, it can happen that you sample some atom types where no valid configuration is available. So we had some more invalid structures in here than for the other experiments.
Also, maybe I can add, sorry, was your question also regarding if we use like bond information in the model, or?
No,
Like
I
how
was
we,
thinking more. I was asking more like, especially because I see that, in these plots the molecule is kind of changing as as you're sampling more. So I was thinking maybe you were doing something with the atom types, but I guess you're essentially keeping the graph fixed at the start and then just learning to generate the conformation.
yes, but we don't give the graph as an input. Like we're not trying to sample a 3D conformer for a specific graph. It's not like we have the connectivity or anything as input to the model.
Okay, I see.
Yeah, so it's not about conformation sampling for a given graph. It's really doing it from scratch. The
Yeah.
only thing that you have to provide are the atom types. So using it as for conformation sampling would be an addition where you somehow would encode this graph information into the model as additional information, but we don't do it.
Okay, and then the validity that you talk about here, is that sort of standard like RD kit, like you then sort of infer the bonds from the conformation and check if that graph of the chemical composition is correct.
Yes, yeah, use RD kit for that.
Okay.
Yeah, do you want to read the question or?
Yeah, so we've got one question in the chat. So he's saying, I see that molecular generation or 3D molecular generation have problems like generating chemically disconnected fragments or chemically disconnected structures. So how can GPFF prevent this from happening? I guess it's kind of related to the validity question as well.
Yes, so I think initially we had some problems with disconnected structures. Which happens if like if you start from this prior with a large noise. So we took a sigma value of 30, which means that the molecules really exploded and all over the place. And then if the first step of this direct denoising is bad, for example, then maybe you will have something which is like some part of the atoms will go somewhere in space beyond the cutoff line, and then you cannot bring it together anymore. But somehow we changed the training to focus a bit more on the intermediate part, and so we sample more structures closer to the minimum, and that somehow prevented this from happening. And I think intuitively what happens is that the model just learns if the noise is very large, it has to bring everything a bit closer together. And as long as that works, you don't have any disconnected structures. So we didn't observe any disconnected structures at all, actually, from there. Only when we... Yeah.
Sorry, I just want to say that, but there's no guarantee. This is just the observation. It's not, there's nothing built in to completely prevent it. So it can happen, but I think in the validity check, we would mark it as invalid if it is composed of two fragments instead of one completely connected structure. So since the validity is so high, there can only be a very small number of molecules at all, if at all. Yeah.
One other question for me is.
Oh wait, we have we have a question from. Yeah, you can unmute yourself if you want.
Yes, thanks for the nice talk. I have a question about this time t. So for this pseudo-force field, you remove time conditioning compared to diffusion model, right? I'm thinking that's implementation details, and some work they also try to remove time directly from the diffusion models that will degenerate the performance. So ideally, I mean, this force field, the things you regress to is also depends on this sigma t. So I'm thinking you can also do this time conditioning, and then you through some reparameterization, you get the equilibrium structure. So I don't know. I don't know if that. Do you think it's possible to add this conditioning back to improve the performance?
Yeah. So we also tried this, but like first of all, we wanted to get rid of the time step and not include it, because if we don't need the time step, we can do all these intuitive steering things, because we can just modify intermediate structures. If you would do that with a standard diffusion model, you would break the schedule, right? So the model would predict something, it would think it's at some time step, and then you modify it, and then you don't know the time step anymore. So that's why we wanted to remove it, but we also tested how this affects the performance. And I think I might have some backup slides somewhere. Yeah, here. So here on the left side, you can see the GPFF model. This is just with two, I forgot to add the labels here. Okay, but like one of them is ancestral sampling and one of them is Hoyne sampling. So it's just two different diffusion-based sampling algorithms. And here we have one model which is time-aware, which is a dashed line. And time-aware means it knows the time step, so we provide it to the model. So this is an extra model that we trained with time step conditioning. And the solid line is the performance of the model that doesn't know the time step. So it doesn't know it during inference and it doesn't know it during training. And as we can see, the results are just the same. So giving the time step as an information doesn't help at all here. But if we do the same thing for a diffusion model, so as I said, the only difference actually is that GPFF learns the magnitude and the direction, and the diffusion model only learns the direction. And if we remove the time step conditioning from the diffusion model, we can see that the performance drops significantly, right? So here on the left side, we have this ancestral sampling generation, and we only get like 60% validity instead of 91. And with Hoyne sampling, interestingly, at larger budgets for function evaluations, we end up in a similar regime, but for lower numbers of function evaluations, the performance is clearly decreased. So this shows that GPFF, it doesn't need the time step, and also time step doesn't help, but the diffusion models need the time step in order to make good predictions.
Okay, thank you.
We have another question online. Yeah.
Okay, thank you. I'm just a random guy, like seeing your LinkedIn post, and I'm working on the same problem. So thank you for your knowledge sharing. Okay, so I have two questions. The first one is the next question from my previous question on the connectivity. So, so what is the problem of connectivity is if the molecules is like fragment, in fragment, usually when you calculate the validity is take the largest fragment and then you calculate the validity based on the largest fragment. So I see this on my own project that even though the connectivity is really low, the validity is still very high. It's because that the calculation is based on the largest fragment. So I don't know if you were like having the same problem as I am. Also, my second question is how does your model produce genuine novel scaffold rather than just interpolate from the memorized equilibria, and can this genuinely generate out distribution by the model itself? My third question is like I'm working with real pharmacists on this drug discovery, and what they really concern is the inhibitor, like the activities of the molecules against a specific target. So usually this is calculated by a matrix called IC15, and I don't know if you are taking into account about this, or essentially you're just focusing on just successfully generate the molecule. So that's my question.
Okay, so let's start with the first question. So it's again on like disconnected molecules and validity, if I understand it correctly. And so in our validity check, if something is disconnected, we mark it as invalid, right? So That means if you look at the numbers and we have like 99% validity, that means if all invalid molecules would be disconnected, it would still be like 1% or something. So this is something which we just don't observe. And also if we like visually inspect the database that we generated, I never saw any disconnected structures using GPFF like we do it here. And yeah, so what was the, I forgot the second question. Sorry.
Yeah. Maybe I can,
yes.
sorry, one addition and also the second question, but first about the first one, I just wanted to note that it depends on how you compute the validity. So I agree previously when using this RDKit function, I think sometimes when you have fragments, it will still say it's valid, but in the smile string that you get, you will see that it's disconnected because there is a dot. I think the dot basically says that these are two systems. So if you don't filter for this, then you can get wrong results. But I think we're basically looking for this in our check. So, but you're right that you have to be careful. If you just take the function, you might get like the wrong impression because you get disconnected things. But if you know about this and then build this into your evaluation script, and this is I think what we did, but maybe we will double check. But I'm pretty sure we captured this case. Then we manually mark it as invalid, even though if maybe RDKit would say these are two valid fragments, like we get a valid smile string made up of two fragments. And then the second question was, I think, about the novelty, like if we know that we actually sample something that is not just the same as the training set. And this is something where we still have to do some more evaluations of the distribution, I think, matching the novelty and the uniqueness. We mainly looked at the validity, and it's true that this is definitely a shortcoming where we have to investigate further to see if there is a certain bias in one of the sampling approaches, or like using the direct denoising or the diffusion-like sampling. Maybe you want to add something on that, Stefan?
No, yeah, this is something we still have to investigate, like the novelty and but if we, I mean, for example, in this example, this aspirin molecule cannot be in QM9, for example, because it has more atoms than QM9 allows. So at least this example shows that we can sample more than just a training set. And also, I think if you look here at this distribution where we did this intuitive steering targeted design for molecular shapes, you can see that there's very few sphere-like structures in QM9, but we can easily sample them here. So it's not proof that we don't sample, that we don't just sample training structures, but I'm very confident that this is not an issue. But we will further investigate this and compare this in direct denoising to diffusion-based sampling also, yeah.
Yeah, thank you for the So thank you for your answers. So I still have like a third question. Do you need me to repeat it?
Yeah, that would be nice. Thanks.
Yes. So I work with like real pharmacists, and what they're concerned about is the activities against specific targets. So it's kind of like the proteins in the cancer, and they want to find like the molecules that can really bind to the proteins, so that the matrix that they use to like calculate the binding is IC50. It's like the inhibited against the target. And have you ever considered about working on this? It's just my question.
Yeah, so I mean, we just showcased a general idea of how we could generate something that would fit the protein pocket using the shape, for example, or using some scaffolds where we know that might fit, but we're not too much into drug design. So we are not very familiar with those protein ligand data sets. So this is something that would be very interesting to try, I think, where you, I don't know, you keep the protein pocket fixed and you just perturb the geometries of the drag candidate, for example, and then you try to sample something, but that fits the shape is, of course, a very interesting application. So yeah, this is just a very simple example of showcasing the methods, but for real applications and protein pockets, it of course makes a difference, like what kind of atoms you have in this protein pocket and how it binds there. So I'm very confident that this is something you could try with this method, but we haven't tried it just because it would be a lot of extra effort for us to get familiar with those kinds of data sets. So yeah, we haven't done this yet.
I think that is for my question. It's I think I will try this model once. It's very interesting. Thank you for your talk.
Thank you.
Thanks.
Yeah, thank you very much for being here, and thank you very much, Stefan and Niklas. I actually had the exact same question about like extending it to conditional generation on protein pockets, and also I was quite interested to hear about whether you were thinking about extending it to larger molecules.
Yeah, so I mean, there's a lot of possibilities where you could try to go from here. We were actually more interested in doing materials generation. And we didn't really want to work on molecules for this project, but in order to do something for materials, you have to do molecules first. And then since the results seem to be good, we thought, okay, we will try to wrap it up and write something about it. But yeah, we probably won't go to larger molecules, and we probably also won't go to protein pockets, although it would be very interesting, I think. There's a lot of, because I think just because it's so intuitive to use, right? You just think of what you want to have. You want some shape here, you want some scaffold there. I think this can be very practical for drug design, although I don't really know how people in drug design work on this problem exactly. But I think it's promising for this. So if you want to try it out, we're happy about it.
Yeah. So thanks everyone for joining, and yeah. So yeah, see you in the next session.
Yeah. Thanks again for presenting. It was very interesting.
Yeah.
Thank you for having us. It was great.
Thank you.